There are two methods for getting chemical formulas from experimental data that we will deal with in this class. So this video is just about elemental analysis. This is a method that uses mass percentages, which we just did in the last video, to take some experimental data and turn it into a chemical formula. So what I'm going to give you first is a strategy. So when you are doing these practice problems, you can just use the beginning part of this video to prompt you for the steps that you need to take until you feel comfortable moving away from these strategy steps, but you'll have the examples throughout the rest of the video in case you need help with a particular part. So our strategy in elemental analysis, what we will be given is a mass percentage. So step one is going to be to turn a percentage into grams somehow, and you'll see this in the specific steps. Step two will be to get grams into moles. Step three is going to be to write a preliminary formula. Step four is going to be to convert our preliminary formula to a formula with integers as subscripts. And this is going to be something called the empirical formula. And then step five, you won't always be able to do, but if you have the molar mass, you can find the molecular formula. So I mentioned empirical formula. We haven't specifically defined this term yet, so we should probably define that before we go into solving this problem. So an empirical formula is a formula that shows the smallest whole number ratios of elements in a compound. So this is kind of like what we talked about when we talked about formula units. But it works for molecular and ionic compounds. So, example, the molecule C2H4 is the molecular formula. But if you look just at the subscripts, it's possible that we could reduce those subscripts. Now, it won't be the same molecule, but it'll be kind of like a base unit of which the actual molecule is some kind of multiple. So if I were to reduce those subscripts, CH2 is the empirical formula. So when we're working with experimental data, we'll always find this empirical formula first, and then if we know the molar mass, we will be able to scale that up to the appropriate size so that we know the actual molecular formula. So I'm going to pause and write out this example, and then we'll go through the steps to take elemental analysis data and turn it into an actual molecular formula. The example that we're going to use says that elemental analysis of a compound with a molar mass of 90.08 grams per mole shows it contains 40% carbon by mass, 6.71% hydrogen by mass, and 53.3% oxygen by mass. Find its molecular formula. So you might be wondering, if we don't know the molecular formula, how on earth do we know the molar mass of this compound? So this is where I tell you that I promise we're not making up these stupid problems with information that you would already know and making you back calculate for no reason. There are other experiments, so stuff like osmotic pressure that we will learn about in Gen Chem 2 that would let you get the molar mass of a compound without specifically knowing its molecular formula. So I promise we could actually get this information, and I didn't make this up just to make your life really difficult. Okay, so step one in our strategy is to turn the percentage into grams. So step one is assume, which is a terrible word to start a step with, but I'm going to explain it, that you have a 100 gram sample. And so even at this first step, why would we do something? How do I know that I need to assume? Why did I pick 100 grams? How do I know how much they put in to calculate the percentages for this sample? You can actually pick any size sample that you want. The thing is, if we know the percentages, every sample size of this compound should have the same percent by mass. If it's a 100 gram sample, well, if it's 40% carbon by mass, it means that my sample had 40 grams of carbon in it. If it's a 1 gram sample, it means that I had 0.4 grams of carbon in it. So it works for any sample size. And if you don't believe me, after we go through this and you know all of the steps, come back and pick a different sample size, literally any sample size you want, and you will get the same answer at the end. The reason that we assume 100 grams is because it makes the math really easy. So if I have a sample that's 40.0% carbon, that means that 0.40 times 100 grams, well, equals 40.0 grams. So my percentages just directly translate to the number of grams of that element in the sample. So 6.71% means that I had 6.71 grams of hydrogen, and it means that I had 53.3 grams of oxygen. All right. Now that I have grams, because I know the molar masses of each of these elements from the periodic table, I can convert those values to moles. So step 2 is where I convert grams to moles. And so again, at this step, you might ask, why are we doing this? I mean, maybe it doesn't have as many question marks as the first time. You were like, why am I assuming the sample? But in this step, we're converting everything to moles because in the chemical formula, which we just looked at in the last video, or maybe it was 2 videos ago, I have no idea, those ratios in a molecular formula are giving you mole ratios. So if we can get these values into moles, we can compare them to each other and come up with the proper subscripts for our actual molecule. So my 40.0 grams of carbon, if I divide that by 12.011 grams per mole, I'll get the number of grams in this sample. Now, if you are coming back through this and doing it with a different sample size, you'll have a different exact number of moles, but the comparisons between them will be the same. 6.71 grams of hydrogen divided by 1.008 is 6.66 moles of hydrogen, and 53.3 grams of oxygen divided by 15.999 is 3.33 moles of oxygen. So step 3 is to write a preliminary formula. And if you are looking at other example videos or practice videos on how to do elemental analysis, you might not see this step. I think this step is really useful to get you into what's beginning to look like a molecular formula, but it's going to look wrong. What I do is I just take the moles we calculated and make them the subscripts, right? Because what we're really looking at, so we're eventually going to look at how these compare to each other, but I have mole values, so I can put them in here as a subscript in my preliminary formula. So carbon with 3.33 of them, with hydrogen at 6.66, and oxygen at 3.33. So again, it looks wrong, but my subscripts are in moles, so it's a good beginning of what my molecule is going to look like. So step 4 is to get this into actual whole number ratios. So this is where we need to convert to integers. The fastest way to do this is to divide each subscript by the smallest number. And then if you have something that's not a whole number at this point, you can multiply back up if necessary to get integers. Okay, so my preliminary formula is the C 3.33, H 6.66. The smallest number is 3.33. So if I divide each one of these by 3.33, I get carbon with a subscript of 1, which you don't have to explicitly write. I'm just going to put it in here for now so that I make sure I don't miss anything. Hydrogen with a subscript of 2, and oxygen with a subscript of 1. So I have integers. I don't need to multiply back up. You will see that done in an example later. But that's it. So CH2O is my empirical formula. So I was able to, we are what, steps 1, 2, 3, 4, and we are given the molar mass. So I can go on and do step 5. Now, if I didn't have the molar mass, this is the most I would be able to do, and that would be my answer. Step 5, we're going to convert to the molecular formula. So this has just a couple of sub-steps. The first is to calculate the molar mass of the empirical. So this is CH2O. So the molar mass of this would be 12.011 plus 2 times 1.008 plus 15.999, which is 30.025 grams per mole. And then the second step is to compare this to the given molar mass. So if they match, it means you don't actually have to do any more work because the empirical formula is the same as the molecular, which is not the case here, right? Our empirical is 30.025 and our molecule was 90.08. So if not, divide to get the multiplication factor. So if we take the actual molar mass and divide it by the empirical, it will tell us how many of the empirical formula units we need to put together to get the entire molecule. So for ours, the actual molar mass was 90.08. The empirical was 30.025. So dividing those gives us 3. So the last step is to actually multiply. So that means I have 3 times as many carbons, 3 times as many hydrogens, and 3 times as many oxygens as I saw in my empirical formula. So my molecular formula is C3H6O3. And what you should see when you get to the molecular formula is that the elements are there in the same ratios, right? If I were to divide all of those through by 3, I'd get back to the CH2O. And if you want to double check that this is actually the correct molecular formula, you could calculate the molar mass of C3H6O3, and you should get 90.08.